I'm Eric.
And I'm Ryan, and today we'll be talking about optimizing energy landscapes in ways that we can increase energy yield and conserve pollinator populations.
We will begin our presentation by detailing the reasons why this study is important, and then we will explain our idea of combining hybridized energy landscapes with novel ecosystems. We will go on to explain how we propose to carry out this idea, as well as what can be done to optimize the results.
Global energy consumption has been increasing over 2 decades and is projected to continually increase into the foreseeable future, as is illustrated by the solid black line in this figure from Nathan Lewis's article, Powering the Planet.
Given such projected increase, a major transition to renewable energy resources is inevitable. Some argue that climate change is a major reason for the transition, since the use of fossil fuels has caused the change in geologic era due to carbon emissions. Others argue that we will run out of fossil fuels, or rather, the cost of extracting them will become more than they are worth selling. Either way, the transition is inevitable.
So it will be very important to assess what the most effective way to carry out this transition will be, because this transition will be expensive. Any mistakes that we make throughout this transition will do nothing but increase the cost. So research should be done to optimize energy production and minimize costs in order to ensure that we do not invest tremendous amounts of resources in a practice that is not worth pursuing, like using corn ethanol as fuel. With proper investments, the benefits of this transition will outweigh the costs.
One of the major things to consider during this transition is energy sprawl, the amount of land that is required to produce a given unit of energy. We do not have unlimited space on the planet, and energy-dense resources allow excess land to be used for housing, food production, or conservation. As is shown in this figure, biodiesel and ethanol use large amounts of land to produce much less energy than renewable sources such as wind and solar photovoltaic.
One way in which energy sprawl can be reduced is by hybridizing energy landscapes to maximize energy output per unit area. In this presentation, we are focusing on hybridizing land within wind farms because wind turbines have a lot of space surrounding them that is not being used for energy production.
We decided to fill the space around turbines with solar panels because the sun is a constant and powerful source of energy, and solar panels produce a lot of energy relative to how much land they use. The map illustrates this by showing how large a square of solar panels would have to be to power each continent.
Furthermore, hybridizing solar and wind power would be efficient because they are complementary in many ways. For example, if there is no wind, the solar panels can still produce electricity. And if there is no sun, the wind turbines can still produce electricity. The turbines do not cast a large shadow, so the solar panels could still be active in the area around them.
Another interesting way to hybridize land is to incorporate novel ecosystems into energy landscapes. In a currently active campaign, a Minnesota group is trying to raise money to advertise their conservation efforts of hybridizing solar farms with pollinator habitats. If their campaign is successful, pollinator populations will benefit and carbon emissions will be reduced.
Pollinators are very important for crop and flowering plant reproduction. They currently pollinate $23 billion worth of U.S. crops per year. Without the pollinators, the plants would not be able to produce enough seeds to sustain their populations. For example, this image of raspberries on the lower right shows how pollinators contribute to fruit health. Unfortunately, both managed and native bee populations have been on the decline in recent years due primarily to habitat loss. The minimum habitat requirements for butterflies are presence of larval food plants as well as adult nectar sources. For bees, nesting sites are naturally patchy and are distant from food sources. Bees commonly travel up to 2.8 kilometers from their nests to find food sources. This means that habitat continuity is not important. The habitat simply must be present.
So our research question is, can we use GIS to site renewable energy resources in ways that are productive and can benefit pollinator conservation?
We used Model Builder to find the best places for wind power in Minnesota. We also found the total area currently available around wind farms for potential energy hybridization. For our calculations on solar energy, values were based on the total surface area of the solar panels themselves, not on the area of land needed. We assumed that the solar panels were 10K solar reflect system panels that were not shaded. All of the calculations were based on a 40 kilowatt model system. For our calculations on wind energy, we created a standard estimated distance between turbines based on a densely populated wind farm, and we assumed that the number of turbines in Minnesota will remain constant.
The model system that we used for our calculations was a 40 kilowatt system located on the roof of the Anderson Student Center at the University of St. Thomas. By using the surface area of this system and the electricity output of this system, we were able to calculate the electricity produced per unit area of a similar system. We found that such a system can produce about 165 gigawatt hours per square kilometer per year.
Minnesota currently produces 4,786 gigawatt hours of energy per year, so it would take 29 square kilometers of solar panels to replace the existing energy production in Minnesota.
To illustrate the energy density of solar panels, here's a map of Minnesota with an area of 29 square kilometers displayed in orange. To put this in perspective, 18 of these squares could fit into Lake Mille Lacs.
The map on the left shows the unused land that we currently have around turbines, which, compared to the orange square taken from the previous slide, is quite a lot of space. The map in the middle shows the optimal locations for turbine placement, and the map on the left shows the locations where solar energy is most abundant. As you can see, the current turbines are already located in areas that optimize wind and solar energy production.
The unused land around turbines was calculated by using a densely populated square kilometer of wind farm. We used GIS to measure the area of the land being used by the turbines as well as the roads required to access them, as illustrated by the blue highlights in this image. We then subtracted this area from the area of the square and divided the difference by the number of turbines in the square to calculate the area available per turbine, or the buffer region, which is approximately 104,244 meters squared.
We propose that this land should be populated with solar panels. This would be efficient because the infrastructure for collecting and transporting electricity has already been constructed. The landowners that have turbines have clearly expressed interest in producing energy, and it would be highly profitable. We acknowledge that in densely populated wind farms, there is much overlap of the regions, making the buffer area larger than reality. However, there are also turbines that are placed with far more space between them, which will balance out these estimates.
So we multiplied the number of turbines in Minnesota and the area of the buffer regions to calculate the cumulative area of the buffer regions, representing the total space available in Minnesota around the turbines, which is 113.52 square kilometers.
If this area was completely filled with solar panels, Minnesota would produce a total of 19,481 gigawatt hours per year when combining the amount of energy produced by wind and solar.
This is a very appealing option, as it would allow Minnesota to reduce the amount of energy it needs to import, or it could sell excess energy to bordering states. Furthermore, it could replace non-renewable energy production. However, we could hybridize the landscape further by including pollinator habitats. In our calculations, we proposed that half of each buffer region could be filled with solar panels, and the other half with pollinator habitat. We acknowledge that splitting the area exactly in half is an arbitrary amount, but even so, this model would produce more energy per year than our current production, and it would give pollinators substantially more habitat.
The new pollinator habitat would provide ecosystem services like carbon sequestration and contaminant filtration, or could be used to graze livestock in times of drought. The habitat would also help to stabilize the declining pollinator populations on which our modern agricultural system relies. In the future, it would be helpful to determine which plants are most effective at providing food for pollinators, sequestering carbon, and providing ecosystem services. Further research could also explore what distribution of land would optimize pollinator habitat and solar energy production.